Now, in this lecture, we'll find out the length of line segment X. In the drawing, we have rectangle ABCD. Inside this rectangle, we have those two circles that are tangent to each other externally at this point, or they are touching each other externally at this point. In addition, we know that line segment EF equals to 6 units in its length. Side AD of this rectangle ABCD equals to 8 units. And our mission is to find out the length of side AB of rectangle ABCD is equal to X units according to what is given us in the question. So we have to find out the length of side AB is equal to X. So first of all, because of the fact that ABCD is a rectangle, we know that all the angles inside the rectangle are right angles. So this angle is equal to 90 degrees inside. This angle also equals to 90 degrees. This angle equals to 90 degrees. Finally, this angle is also equal to 90 degrees in its side. We define the center of this small circle, this point as P. We define the center of this circle, this point as Q. And the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 11. According to rule 11, the perpendicular to a chord drawn from the center of the circle bisect the chord. So in the drawing we have a circle, the center of this circle is here at point O. From the center of this circle, that is to say from point O, we draw perpendicular on chord AB. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB as point M. So OM is perpendicular to chord AB. And whenever you draw a perpendicular from the center of the circle towards any chord, it bisects the chord. So the perpendicular OM bisects chord AB. That is to say AM equals to MB. Okay, a perpendicular from the center of the circle towards any chord bisects the chord. In this case, the perpendicular OM, that is from the center of the circle, that is to say from point O, bisects chord AB. That is to say AM equals to MB. Can implement rule 11 in our drawing. So, from the center of this small circle, that is to say from point P, we draw perpendicular on this chord. We define the touching point between those two circles as point S. So this is chord ES inside this small circle. From the center of this small circle, that is to say from point P, we will draw perpendicular on chord ES. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P on chord ES as point M, and according to rule 11, the perpendicular PM bisects chord ES. That is to say, EM equals to MS. Repeat again. EM equals to MS. According to rule 11, line segment EM equals to line segment MS. Okay, according to rule 11. Likewise, from the center of this big circle, that is to say from point Q, we will draw perpendicular on chord SF. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q on chord SF as point N, and according to rule 11, the perpendicular QN from the center of this circle, that is to say from point Q, bisects chord SF. That is to say, SN equals to NF. Repeat again. Line segment SN equals to line segment NF according to the same rule, rule 11. It has given us the question that the length of line segment EF is 6. EF equals to 6. EF equals to 6. EF, this is line segment EF. EF equals to EM plus MS plus SN plus NF. Repeat again. From the domain, it is very easy to see that EF equals to EM plus MS plus SN plus NF. Here, EF equals to EM plus MS plus SN plus NF. So here MS equals to EM. So we can substitute EM here by MS because EM equals to MS. So we substitute EM in this equation by MS because MS equals to EM. And we get that EF equals to EM is MS plus MS plus SN plus NF. But NF equals to SN, so we can substitute NF by SN. We substitute NF by SN. So in conclusion, found out that EF equals to MS plus MS is 2MS plus SN plus SN is 2SN. So EF that is equal to 6, it is equals to 2MS plus 2SN. Here we'll divide this equation by 2, and finally we'll get that 6 over 2 is 3, so 3 equals to MS plus SN. we found out that ms plus sn, ms plus sn is equals to 3 units. But ms plus sn is mn. Okay? ms plus sn is mn. So, in conclusion, from this equation we derive that mn equals to 3. Here, mn equals to 3. Here, this line segment mn equals to 3 units in its length. Okay. In the next step, we define the point of tendency of tangent AB with this small circle as point K. We join points P and K together by a straight line. What is the definition of line segment PK? Line segment PK starts from point P, that is the center of the small circle, and ends at point K, that is the point of the small circle itself. This is exactly the definition of a radius. So PK is the radius of this small circle. We will define the radius of this small circle as A. Therefore, PK equals to A. According to our definition, it is the radius of the small circle. So here we have the radius pk that is drawn to point K, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius KP. If AB is perpendicular to KP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. We will define the point of tendency of tangent AD with this small circle as point H. In the next step, we will join points P and H together by a straight line. PH is the radius of this circle that is equal to A according to our definition. The radius PH is drawn to point H, that is the point of tendency of tangent AD with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius HP. If KP is perpendicular to HP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. So inside this small quadrilateral AKHP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles inside this small quadrilateral AKHP to 360 degrees, the missing angle here must be equal to 90 degrees in its size. So inside this small quadrilateral AKPH, we have 4 right angles. Therefore, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral AKHP as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle HPKA, side HP must be equal to the opposite side AK. But HP is A, therefore AK is also A. Likewise, according to the same rule, in rectangle AKHP, side KP, side KP must be equal to side AH. KP is A, therefore AH must be also equal to A. So actually found out that the quadrilateral AKPH is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this quadrilateral is equal to A, therefore this quadrilateral is a square. In the next step, we'll extend the radius KP that is equal to A by a straight line until it touches side DC. We extended the radius KP that is absolutely a straight line by straight line. When we extend a straight line by straight line, the result is a straight line. Here we define the touching point of the extended radius KP with this side DC is point Z. We extended the radius KP by straight line and the result is KZ. Therefore KZ, it is absolutely a straight line also. By doing this construction, we created the big quadrilateral AKZD. Inside this big quadrilateral AKZD, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So, inside this quadrilateral AKTZ we have 4 right angles. Therefore, we relate to this quadrilateral as a rectangle, because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AK must be equal to the opposite side DZ. But AK is A, therefore DZ must be also equal to A. Likewise, according to the same rule, in rectangle AK DZ, side AD must be equal to the opposite side KZ. But AD is 8, therefore KZ must be also equal to 8 units in its length. KZ equals to 8 units in its length. In the next step, we will define the point of tendency of tangent BC with this big circle SL, and we'll join points Q and L together by straight line. QL is the radius of the big circle. We'll define the radius of this big circle as B. So QL equals to B according to our definition. It is the radius of the big circle. The radius QL is drawn to point L, that is the point of tendency of tangent BC with this big circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LQ. If BC is perpendicular to LQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will extend the perpendicular QN by a straight line until it touches side AD. And we define the touching point of the extended perpendicular QN if side AD is point G. So, by doing this construction, we created quadrilateral GLCD. Inside this quadrilateral GLCD, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees. So, quadrilateral GLCD that has 4 right angles, we relate to it as a rectangle. and we know that the opposite sides of a rectangle are equal to each other. So side DL equals to side DC. Here we define the intersection point between the extended perpendicular QN with side KZ. This point is point S. So inside the small quadrilateral DSDZ, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So we can relate to this small quadrilateral DSDZ as a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. And so in rectangle GSDZ, side DZ must be equal to the opposite side GS. But DZ is A, therefore GS must be also equal to A. We extended the perpendicular QN by a straight line and the result is QG. When you extend the straight line by a straight line, the result is a straight line, so QG is one straight line. So if you focus on the lower side of the straight line QG at point S, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line QG at point S? We have this angle that is 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to the rule that I mentioned, that the sum of the angles on one side of a straight line is equal to 180 degrees. So the missing angle must be equal to 90 degrees. In order to complete the sum of the angles in the lower side of the straight line QG at point S to 180 degrees, the missing angle must be equal to 90 degrees. Here, we actually extended the radius KP of this small circle by a straight line, and the result is KZ. When you extend the straight line by a straight line, the result is a straight line, so KZ is a straight line. So if we focus on this side of the straight line KZ at point S, the sum of the angles here must be equal to 180 degrees. According to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line KZ at point S? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. So the missing angle must be equal to 90 degrees. Again, we extended the perpendicular QN by a straight line, and this way we got the straight line QG. So if you focus on the upper side of this straight line QG at point N, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of the straight line QG at point N? We have this angle that is equal to 90 degrees plus the missing angle. In total, it must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees. So, inside quadrilateral PMNS, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 100. The sum of the angles in any quadrilateral is equal to 360 degrees. So quadrilateral PMSN is 4 right angles, therefore we can relate to this quadrilateral as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle PMSN, side MN must be equal to the opposite side PS. But MN is 3, therefore PS must be also equal to 3 units in its length. We already found out that the straight line KZ equals to 8 units. So Kz equals to 8, but Kz also equals to Kp, that is A, plus Ps, that is 3, plus Sz, plus Sz. So here we know that DC is one side of rectangle ABCD, therefore it is absolutely a straight line. So if you focus on the upper side of the straight line DC at point Z, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of DC at point Z? We have this angle that is 90 degrees, plus the missing angle. In total they must be equal to 180 degrees. So the missing angle must be equal to 90 degrees. We define the point of tendency of tangent DC with this big circle as point T. We join points Q and T together by straight line. QT is the radius of the big circle that is equal to B according to the definition. The radius QT is drawn to point T, that is the point of tendency of tangent DC with this big circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius TQ. If DC is perpendicular to TQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay. So inside the quadrilateral SQZT we have 1, 2, 3 angles. The fourth angle must be also equal to 90 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral SQZT we have 4 right angles. Therefore, can relate to this quadrilateral as a rectangle. And you also note that the opposite sides of a rectangle are equal to each other. So in rectangle SQZT, side QT must be equal to the opposite side SZ. But QT equals to B, therefore SZ must be also equal to B. So we found out that SZ equals to B. So 8 equals to A plus 3 plus SZ, that is B. So in conclusion, we found out that S equals to A plus B plus 3. Here we subtract 3 from this equation, and we get that A plus B equals to 8 minus 3, that is 5. So A plus B equals to 5 units. A plus B equals to 5 units. In the next step, we join points P and Q together by a straight line. But before that, I will present to you a new rule. This is actually rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together must pass through their touching points. So in the drawing we have those two circles that touch each other externally at point P. That is to say that you have an internal notch between them at this point P, or they touch each other externally at point P. And according to this rule 10, the straight line that connects their centers together, the center of this big circle is there at point O, the center of this small circle is there at point M, and the straight line that connects their centers together is the straight line MO, and according to this rule 10, the straight line MO must pass through their touching point, that is actually point P, or MPO is one straight line. Again, MPO is one straight line. So we can implement rule 10 in our drawing. Well, because in our drawing, those two circles have an external notch between them at point S. That is to say, they touch each other externally at point S. the center of this circle is there at point P. The center of this big circle is there at point Q. And the straight line that connects the centers together is the straight line PQ. And according to rule 10, the straight line PQ must pass from point S, that is their touching point, or PSQ is one straight line. So according to rule 10, PSQ is one straight line. So, what is the definition of line segment PS? Line segment PS starts from point P, that is the center of this small circle, and ends at point S, that is the point of the small circle itself. This is exactly the definition of a radius. So PS is the radius of this small circle, that is equal to A. What is the definition of line segment SQ? Line segment SQ starts from point Q, that is the center of the big circle, and ends at point B, that is the point on the big circle itself. This is exactly the definition of a radius. So QS is the radius of this big circle, that is equal to B. So in conclusion, found out that because of the fact that PSQ is one straight line, it means that PQ will be equal to PS plus SQ. That is to say, PQ equals to PS, that is A, plus SQ, that is B. So in conclusion, found out that PQ equals to A plus B. So write it down. PQ equals to A plus B. So write it here. Repeat again. We actually found out that PSQ is one straight line. And that is the reason, because of the fact that PSQ is one straight line, it means that PQ will be equal to PS plus SQ. For that reason, PQ equals to PS plus SQ. So PQ equals to PS, that is A, plus SQ, that is B. So we found out that PQ equals to A plus B. PQ equals to A plus B. But we have already found out that A plus B equals to 5. So we can write here that A plus B equals to 5. And from this equation, PQ equals to A plus B equals to 5, we will derive that PQ is also equals to 5. PQ equals to 5. Here, PQ equals to 5 units. In the next step, we'll implement the Pythagoras theorem on the right green triangle PSQ. So I'll copy the right green triangle in a new page and we'll implement on it the Pythagoras theorem. Here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle PSQ with the curvature from the original drawing, according to the Pythagoras theorem. In this right triangle PXQ, PQ squared equals to PS squared plus SQ squared. PQ is 5, therefore PQ squared is 5 squared, that is 25, and it is equal to PS squared. PS is 3, therefore PS squared is 3 squared, that is 9, plus SQ squared. So 25 equals to 9 plus SQ squared. Here we subtract 9 from this equation, and finally we get that 25 minus 9 is 16, so 16 equals to SQ squared. Here we take a root out of this equation, and finally we get that SQ equals to the square root of 16, that is 4. So here SQ, this line segment SQ is equals to 4 units in its length. The next step will focus on this quadrilateral ABGL. Inside this quadrilateral ABGL, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. This angle must be equal to 90 degrees. So inside this quadrilateral ABGL, we have 4 right angles. Therefore, we can relate to this quadrilateral ABGL as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So I write it down. Quadrilateral ABGL is a rectangle. So the opposite side in the rectangle ABGL are equal to each other. That is to say, side AB must be equal to the opposite side, side GL. AB equals to GL. But AB equals to X according to what is given in this equation. So we can write here that AB equals to X, and from this equation X equals to AB equals to GL, we derive that X also equals to GL. X equals to GL. So what is the length of side GL? GL, X equals to GL, and GL equals to A plus 4 plus B. In conclusion, found out that X equals to GL is equal to A plus 4 plus B. So X equals to A plus B plus 4. X equals to A plus B plus 4. We have already found out that A plus B equals to 5. So we can substitute A plus B by 5 in this equation. So X equals to A plus B, and A plus B is 5 plus 4. So X equals to 5 plus 4, that is 9. So X equals to 9. So we found out that the length of line segment AB is equal to X is equal to 9 units. And that is the answer to our question. In the next step, I will summarize the lecture. So, in this lecture, found out the length of this line segment AB is equal to x. In the drawing, we have a rectangle ABCD. Inside this rectangle ABCD, we have those two circles that have an external length between them at this point. That is to say, they touch each other externally at this point. And actually, line segment EF passes through their touching point. Again, line segment EF passes through their touching point. In addition, we know that line segment EF equals to 6 units in its length, line segment AD equals to 8 units in its length, and again, our mission is to find out the length of line segment AB that is equal to x. So, first of all, we know that ABCD is a rectangle, and we know that that all the angles inside the rectangle are right angles. So those four angles, they are all right angles. They are equal to 90 degrees in their sizes. Each angle equals to 90 degrees. Because of the fact that ABCD is a rectangle. We defined the center of this circle, this point is P. We define the center of this circle, this point is Q. In the next step, I presented to you a new rule and implemented the new rule in our drawing. According to the new rule, the perpendicular to a chord drawn from the center of the circle bisects the chord. In the drawing we have a circle. Inside this circle we have chord AB. The center of this circle is here at point O. From the center of this circle, that is to say from point O, we draw perpendicular on chord AB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB is M. So OM is perpendicular to AB according to our construction. So according to this rule 11, the perpendicular OM on AB, on chord AB, is also bisect chord AB. That is to say, AM equals to MB. Again, AM equals to MB according to this rule 11. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. Here, the perpendicular OM bisects chord AB. That is to say, AM equals to MB. You can implement rule 11 in our drawing. Why? Because in our drawing, from the center of this small circle, that is to say from point P, we draw perpendicular on EF. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point P on EF as M. According to rule 11, the perpendicular PM bisects chord ES. That is to say, EM equals to MS. Repeat again, according to rule 11, EM equals to MS. Likewise, from the center of this big circle, that is to say from point Q, we draw perpendicular on on chord SF. Again, from the center of this circle, that is to say from point Q, we draw perpendicular on chord SF. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q on chord SF as N. So according to rule 11, the perpendicular QN bisects chord SF. That is to say, SN equals to NF. Repeat again, according to rule 11, SN equals to NF. It is given us the equation that the length of this line segment EF equals to 6. So EF equals to 6. But EF also equals to EM plus MS plus SN plus NF. Again, EF also equals to EM plus SM plus SN plus SF plus NF. Okay, again, from the drawing it is very easy to see that EF equals to EM plus SM plus SN plus NF. We have already found out that EM equals to MS. So we can substitute EM in this equation by MS. We did it here, we substitute EM by MS. So EF equals to EM, that is MS, plus MS, and we have plus SN, and we have already found out that SN equals to NF, according to rule 11. So we can substitute NF in this equation by SN, because SN equals to NF. So we substitute NF by SN. In conclusion, found out that EF equals to MS plus SN plus SN. So EF equals to MS plus MS, that is 2MS, plus SN plus SN, that is 2SN. So in conclusion, found out that EF equals to 2MS plus 2SN. Here we divided, we know that EF equals to 6, so we substitute EF by 6, and found out that 6 equals to 2MS plus 2NS. Here we divided this equation by 2, and finally found out that 6 over 2 is 3. 3 equals to MS plus SN. So MS plus SN equals to 3. MS plus SN equals to 3. Okay. But MS plus SN is MN. Again, MS plus SN is MN. MS plus Sn is Mn. So we can write down that Mn equals to 3. From this equation we derive that Mn equals to 3. Here, this line segment Mn equals to 3 units in its length. Okay. In the next step, I presented to you a new rule and actually before that we actually we already found out that quadrilateral AKHP is a square, and therefore all of its sides are equal to each other, they are equal to A. Then we extended the radius KP by a straight line, and we have already found out that quadrilateral AKDZ is also a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side AK equals to side DZ, side AK equals to A, therefore side DZ must be also equal to A. According to the sum rule, side in rectangle AKDZ, side AD must be equal to side KZ, but AD equals to 8, therefore KZ must be also equal to 8. And then we extended the perpendicular QN by straight line until it touches, we actually extended the perpendicular QN in both sides by straight line. We extended the perpendicular QN towards side BC, and we extended the perpendicular QN towards side AD. In this way we created quadrilateral GDCL. Inside this quadrilateral we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral GDCL is a rectangle, and inside this quadrilateral GSDZ we have 4 right angles, therefore side DZ equals to side GS, but DZ equals to A, therefore GS must be also equal to A. And quadrilateral SZTQ is also a rectangle because it has 4 right angles, and therefore in rectangle SQTZ, side QT must be equal to side SZ, but QT is B, therefore SZ must be also equal to B. Then I presented to you, and here we have already found out that KZ equals to 8. What is the length of KZ? From the drawing it is very easy to see that KZ equals to A plus 3 plus B. The reason that PS equals to 3 is because of the fact that PMSN is also a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side MN equals to side PS. But MN equals to 3, therefore PS must be also equal to 3. So we can find out that KZ that is equal to 8, it is equal to A plus 3 plus B. So KZ equals to A plus B plus 3. Or KZ that is equal to 8 equals to K plus 3 plus B. KZ is 8, so 8 equals to A plus B plus 3. Here we subtract 3 from this equation, and finally found out that A plus B equals to 5. A plus B equals to 5. Then I presented to you rule 10, and we implemented rule 10 in our drawing. According to rule 10, if two circles touch each other externally, that is to say they have an external edge between them, then the straight line that connects their centers together must pass through their touching points. So in this drawing we have those two circles that touch each other externally at point P. So they have an external edge between them at point P. The center of this big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects their centers together is the straight line MO. And according to this rule 10, the straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. MPO is one straight line. So we can implement rule 10 in our drawing, because in our drawing we have those two circles that have an external edge between them at point S, that is to say they are touching each other externally at point S. Therefore, according to rule 10, we know that the center of this small circle is here at point P. The center of this big circle is here at point Q. And the straight line that connects their centers together is the straight line PQ. And according to rule 10, the straight line PQ must pass through their touching point, that is point S. So PSQ is one straight line. PSQ is one straight line. Yeah, according to rule 10, PSQ is one straight line. And because of the fact that PSQ is one straight line, it means that PQ, the length of PQ will be equal to PS plus SQ. Okay, PQ will be equal to PS plus SQ. PS is the radius of this small circle, that is A, and SQ is the radius of this big circle, that is B. So here PS is A and SQ is B. So we found out that PQ equals to A plus B. Here PQ equals to A plus B. But we have already found out that A plus B equals to 5. Here. So we can write here that A plus B equals to 5. And from this equation, PQ equals to A plus B equals to 5, we will derive that PQ equals to 5. Here, the hypotenuse PQ of the right triangle PSQ equals to 5 units in its length. Here, PQ, the hypotenuse PQ equals to 5 units in its length, and PS equals to 3. In the next step, actually copied the right triangle PSQ in a new page, and we implemented on this right triangle PSQ the Pythagoras theorem. This is the right triangle PSQ that I copied from the original drawing. The hypotenuse PQ equals to 5, PS equals to 3. According to the Pythagoras theorem, PQ square equals to PS square plus qs squared. pq is 5, therefore pq squared is 5 squared, that is 25, and it is equals to ps squared. ps is 3, therefore ps squared is 3 squared, that is 9, plus qs squared. So 25 equals to 9 plus qs squared. We subtract 9 from this equation, and finally found out that qs squared equals to 25 minus 9, that is 16. So 16 equals to qs squared. We took a root out of this equation, and finally found out that qs equals to the square root of 16, that is 4. If qs equals to 4 units in its length, here qs equals to 4 units in its length. So we have here quadrilateral ABGL. Inside this quadrilateral ABGL we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral ABGL we have 4 angles. Therefore we can relate to this quadrilateral ABGL is a rectangle. Quadrilateral ABGL is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB must be equal to the opposite side GL in rectangle ABGL. Here, AB equals to GL. But it is given us the question that AB equals to X. So we can write here that AB equals to X. And from this equation, X equals to AB equals to GL, we derive that X equals to GL. X equals to GL. So what is the length of line segment GL? From the drawing it is very easy to see that GL equals to A plus 4 plus B. Again, GL in total equals to A plus 4 plus B. GL equals to A plus 4 plus B. Repeat again. GL equals to A plus 4 plus B. So GL equals to X. So X equals to A plus B plus 4. And we have already found out that A plus B equals to 5. So we can substitute A plus B in this equation by 5. And found out that X equals to A plus B, that is 5 plus 4. So X equals to 4 plus 5, that is 9. In conclusion, found out that the length of this line segment AB is equal to X, it is equal to 9 units. And that is the answer to the question. The length of line segment AB, X equals to 9 units. Okay, thank you very much.